So yeah, let's finish up these slides. So we talked about horrible things, issues with computers, and then we slowly started talking about like how do we fix the issues? How do we make sure that programs work when we write them? How can we gain confidence in them? And one way is testing. The other way is verification. All right, so let me show you those words. It's a different word. There are ways to make software that is correct from the start, and it's really interesting that this is possible. It takes a lot of math to make this happen, and so you'll have to wait till like CSCI 26 to fully understand this if you want to. But yeah, there's ways, and so here's some ways that people make correct software, like on an airplane. Hopefully, you don't want anything to go wrong when you're using like autopilot or something. So how do they program that? Stuff that needs to be very, very safe. Today's cancer machines. So yeah, one way to do it is to make programs that are redundant. You make send two versions of the same program into the computer. Have one team work on the first version, have another team completely separate from that first team work on the same program, and then bring them together and have them like run them both, have them agree on the output. That's what's going on in airplanes. Like, you have two different versions of like autopilot software, and if one says to go left, you better make sure the other one also says you should go left right now. If they ever disagree, then like alarms get raised. So that's kind of nice. There's also there's ways to check your work too when you're writing outputs. Like I've shown you how to check your work for certain mathematical problems that we learned about in this class, like base conversion. And so sometimes it's easy to check your answer and make sure it was correct. And so there's programs that do that as well. So that's one way to do it. Just like write a bunch of programs or have programs that check things. You can also get mathematical and like write proofs for your program, making sure that they're never going to hit the wrong spot. All right, and so those go hand in hand with things called analyzers, which are kind of like proofs are baked into them, and they're running your program in a mathematical way to figure out like could anything go wrong right now. And one way to prove programs is correct is to write your program in a special proof kind of language, and there's things called proof assistants that help you do that. This is one popular one. It's pronounced like Coke because it's a French term. So that's pretty funny. But here's kind of how you would prove a program correct. Watch. Here's like 2 lines of Python code. I think you can imagine that this is very easy to reason about, but this idea generalizes. So like these 2 lines of code, I think you can imagine that there's a way to mathematically prove for sure that x is totally 43 right here. Yeah? And then you can prove stuff about like if statements and eventually loops once you learn about those. So that's a thing. That's totally a thing that you can keep going with, and that's what people do when they're trying to prove programs correct. So you can see like the kind of reasoning that needs to take place, like the values of all the variables, how do they change after each line. You have to like mathematically specify what does the line x equal x plus 1 mean. That's kind of interesting. Okay. Yeah, so proofs and analyzers, they kind of go hand in hand. Analyzers have been proved correct in a sense. You can also specify what your program should do in what's called a specification language, and that's where you like specify what needs to happen. You plan out exactly how your program needs to do all the things, and then you can go and verify that your program eventually matches that specification. Okay. So like here's something you could write down if you're coming up with a design for your program. Like people get in a room and they design like what are all the requirements, what are the specifications that our program should follow. So maybe like the output should always be within some range. And then you'll go and you'll make sure your program can never be outside that range. So maybe the output should always be like greater than or equal to 42, something like that. That's like a specification of a piece of a program, okay? And so that's something that people can write ahead of time, and then they can go and make sure with like a proof or an analysis to confirm that this really did happen, okay? So this is fun. It's very fancy. This is something that I studied a little bit in grad school. I'm interested in it, but I can't really give you the full picture until you've learned more about computer science. But I think you can imagine that there are bugs that can arise when you're trying to prove software correct that are different than normal bugs. Like you are required for all of these, not just when you're using a specification language, to specify, you have to design your program in math essentially. You have to specify upfront exactly what your program can do, what it's eventually going to do, all the possibilities. You have to say exactly what's going to happen in your program. And what if you get that wrong? What if there's an error in your specification? You proved your program correct with respect to that specification, but still the specification was wrong, and so the whole thing's wrong. So yeah, your specification can still be wrong, which is a new kind of issue, which is fun to think about. But that's how you can make sure that programs are correct, right? So that's one way people do things that keep our lives simpler and keep us safe. So this is stuff that people do for mission critical software, like on rockets and in airplanes. So speaking of airplanes, let's talk about a system that is within every airplane these days. It's so cool, so advanced. So you know that when you're flying, there's all the pilots are talking to the air traffic controllers, right? They're keeping everybody safe, telling them where to fly, giving them permission to land and stuff. There used to be a thing, or there still is this thing. It's called the Traffic Collision Avoidance System. It's a box within everybody's plane. They all have one of these. It's like TCAS for short, or TCAS, however you want to pronounce it. These exist, and what this box does, is it's like sending out little radio signals, and the other boxes and everybody else's planes are reading them and also sending their own out. And it can figure out if two planes are so close and they're flying in the same direction that they're going to hit each other. All right. So this box is about collision avoidance, and it tells the pilots the box starts making noise, and it's like, you better fly. It's like if it notices that two planes, one flying this way, one flying this way, and they're about to hit each other, it gives you some time to fix it, of course. It says to the first plane, you need to increase altitude, you need to decrease altitude, stuff like that. And so that's what the box does. And unfortunately, the first version of the TCAS system had a bunch of false alarms. And so even when the planes weren't going to crash, it said that you're gonna, and so you better do these things. And so it kind of like cried wolf, and people stopped listening to it, sadly. So eventually they got they ironed out all the kinks, and they got the program working good, and it was perfectly accurate. It was always going to do the right thing and make sure, like, really when you needed to do something, it told you to do something. And sadly, there was a collision. A collision between two planes happened when one pilot, they obeyed the system, the TCAS system, telling you, like, increase altitude. And then the other pilot, sadly, ended up ignoring the system and following the guidance of an air traffic controller who didn't, like, know what the box was saying to the other guy. So they both went up rather than one going up and one going down. So they ended up hitting each other. Pretty tragic. And that goes, and now, like, by law, everyone is required to disobey the human air traffic controller and always follow the TCAS system, which is really interesting to think about. So now, like, it's a program that has the final say over what you do to stay alive. Isn't that cool? Isn't that interesting? So it's unfortunate that it had a lot of false alarms at the start, but this is a good example of us relying on software to make us safer, in a sense. But there's also, like, there were bugs in old things. We talked about the S24. You wrote an essay on that, right? So there's two sides to that coin. Like, should we be trusting software with our lives like this? And so let's have a little mini debate right now. We've given a lot of information about these kinds of things. I've refreshed your memory on them. But please, let's get into little peer instruction groups. Go to that written ice page, and let's enter in some ideas. Let me clear it out for us. Boop. Post not found. So here's my question for you guys to discuss as a group. Do we depend on computers too much? Like, they're everywhere. They're used in health. They're used in automation or transport, stuff like that. Try to write one good argument, at least one good argument for, yes, we do depend on computers too much, and one good argument for no, we should be depending on computers, and here's why. All right, try to explain your answer. So give me an argument for and an argument against. It's a good job. It's a good way to strengthen your critical thinking skills. Even if you think one way very strongly, I still want you to think about the other side. All right? So take a few minutes to discuss that. is the alternative, right? Trusting a human over a computer. You may be biased because you're in this class. Still think about the other side, though. All right, another minute or so to get something in there, please. So I want this as an SVG. Do you open it? So yeah, please take another few seconds to get those thoughts in there and press submit. And then I'll have to work on that later today. Yeah, see what we're thinking. Good job with your two ideas. So yeah, let's take a look. Group 16. Yeah, we maybe should rely on more because computers they're very good at doing math, right? They're very good at computation. For the things that they can do well, they do it very quickly, much faster than any human could. And so I like that idea, more objective decisions, because like there is the human factor that humans like to think about. Maybe computers, yeah, technically they could be programmed to be more objective about things because they're not like best friends with anybody. They're not like getting more money if they do one thing a certain way. So that's a very interesting argument. I like that. And yeah, so I like the other side as well. So like there's always like bugs and things that are vulnerable inside of every program. You can always usually hack one if you really wanted to. And so maybe it would be better to just like not have computers for those reasons. So I like it. Yeah, let's take a look at let's go back down to the bottom, group 18. Rely too much on computers where sex or society are losing basic understanding of processes due to allowing computers to do everything. That's very true. Yeah, so like think about calculators for an example. Like I guess if we really wanted to, we can all do long division. It would take us a while, but like I could not do it fast anymore. Maybe that's a problem. Maybe there's other things like that we can't do well. Spelling as well is a big thing. Like we're all typing on a computer nowadays, and like our issues get either auto-corrected or underlined so we can fix them. Like back in the day when you had to write essays on paper, like we all knew how to spell. Maybe we don't anymore. So yeah, I like that expertise is being lost to computers. What if they ever go away? I like it. And yeah, again, computers are faster at certain things. They're better at humans. They're less error prone. Giving the right amount of medicine, they'll make sure that they're never going to ruin things. Better to let the computer do something rather than a human because they're better at math and less likely to make mistakes. I like the medical idea, definitely. Yeah, so these are really good thoughts. I'm glad you guys took the time to come up with those. Yeah, any questions, comments about the things that you saw your peers write? Very, very nice. So yeah, make sure to do attendance. I'll stop that in just a second. But thank you for your thoughts there. I don't want to move the tab. There we go. Yeah, let's keep on trucking then. So yeah, the question is like, do we depend on computers too much? So I don't know. There's definitely two sides to the coin. Like with the air traffic example, the TCAS system, maybe like we should depend on them more because like they're going to prevent issues. If you get the program right, like they're going to save lives. So that's really nice. Yeah, so we could always ask our boys about the problem because this is technically an ethical question, right? Like computers, should we be using them a lot or a little? Not at all, maybe. What would Kant say? He would be like, he would be asking the question, should we always, he used the word always, right? Should we always be looking to computers to like solve all of our problems, to do everything for us? And he's a big proponent of individual rights, right? So he'd be like, if you didn't want to do that thing using a computer, like if you wanted to do your math by hand, like that's fine. Nobody's going to force you to use it. So I think Kant would not be about using computers all the time. Like he'd be pro-choice for this idea. And so you could see him arguing either side, like maybe use the computers for things that computers are good at. And then a utilitarian like Mill would say something like, yeah, look at where we were 100 years ago without computers. The way the medical field was, the way education was, just all these things. Look at how they have improved the access to information that we've gained over time. Like, we should never get rid of computers. I would see a utilitarian saying that no matter what, most likely. Okay? I hope you see that. I'm sure you can find a way to talk about the issues, like talk about the Therac 25 stuff. You can also maybe think that a utilitarian would, like, you could weigh those things. I could see it would take some arguing, but you could think of like maybe they should be limited and come there with a utilitarian argument. But I would think that utilitarians would be pro-computers. And so yeah, computers, like we're not getting rid of them anytime soon. So like, do they really make us safer? Let's see what they're doing. So like in cars, we have computers, tiny little microchips all over the place to make us safer. There's ABS, right? That used to not be standard on cars. You used to have to like, I remember watching a driver's ed video where like they're telling you to like pump your brakes if you don't have ABS, anti-lock brake system in your car, right? Nowadays it just does that for you, and so you don't skid when you have to like slam on your brakes, which is really nice. Every car these days has like a check engine light. That's a little computer running little tests to make sure everything's okay, instead of just your engine blowing up one day, right? So that's really nice that we have that. So it's definitely keeping us safer. Not to mention that like the whole crash test simulations, maybe that's making us safer in the first place. Airplanes, they have the TCAS system to make sure you don't crash. They have the autopilot system to make sure you don't get so tired that you crash. Nice stuff like that. Making sure that everybody is safe up in the air. Everybody these days, a lot of people like have the little Ring doorbell camera and stuff. There's like home security systems are a thing. They're all electronic. They're technically using tiny computers, right? Your little password, stuff like that. I guess the security system that everybody had before computers were a thing was just like you own a bunch of dogs, right? That was your home alarm. But nowadays, like the fire department will come if, or the police will come if like your alarm goes off and you don't like put in your code. Your phones are technically more secure because they're backed by passcodes that like nobody can like guess your password and then go and look into your bank account information because you most likely have a bank app on your phone, right? And then speaking of banking, like you can do it online these days. You used to have to like go in person. It's really nice, right? The two-factor authentication, making sure it's you. Back in the day, like this was well before my time too, but if you were a college student, you'd have to go in person to sign up for your classes. You have to fill out a piece of paper with what classes you wanted and then pray that you got those. Nowadays, you can sign up for classes online and see which ones are empty and full just at the blink of an eye. That's super nice as a student, right? I don't know if that's making us safer, but it's definitely a convenience thing. A lot of these are convenience things as well as safety things. So that's pretty cool to think about. So yeah, just a bunch of ideas for the day. Questions, comments about that before I switch gears to a different topic? Alright, so I would like to go to a new set of slides. I want to talk about artificial intelligence, which is a very fun topic to talk about. It's definitely in the public eye these days, so it's something that's relevant, and I'm sure you've heard a lot about it. So let's take a deeper dive than maybe you have yourself. So I'm excited. To get there, we need to talk about. It's not really a law; it's like a hypothesis. The full name is called Moore's Law. I'll tell you about it. It's an interesting idea. It's answering the question of like how fast are computers getting faster? Because like to do artificial intelligence, you need a powerful computer. Computers didn't used to be so powerful. So like how fast are they getting faster, more powerful? I promise that's a question that you might want to ask. And so Moore's Law was just an observation that this dude whose last name was Moore came up with. This was invented or coined by a dude named Gordon Moore. He was the co-founder of Intel, very, very important company. He noticed that the number of transistors inside of a microchip doubles around every 2 years. So that's kind of nice. So number of transistors doubles. So like, I don't know, year 1, you have 1 transistor. Year 2, you have 2 transistors. And then year 3, you have 4 transistors. And just like after that, you get to 8 and 16 and 32. And they keep doubling at an exponential rate. Okay? And for a while, that doubling of transistors, we talked about a little bit what that means. Just a little, it's like a really cool, tiny electronic switch. For a long time, this meant that computers, every time that they had double the transistors, they also got twice as fast, which is nice. So the way that we measure speed of a processor is in hertz. And so like maybe you have a 2 gigahertz processor in your computer. Like the fastest ones we have these days are about 4 gigahertz, I would say, consumer grade, if you don't overclock them at least. And so eventually, this didn't actually. We still are usually doubling the amount of transistors every about 2 years. So Moore's Law is still applying to us, but computers are not getting twice as fast every 2 years nowadays, unfortunately. We had 4 gigahertz processors back in the early 2000s, totally. So the reason we can't like make 8 gigahertz, 16 gigahertz processors, which can do like, what the gigahertz means is like you can do 4 billion operations inside of a processor a second. eventually there were power issues. We started running into power limits for our processors. And so, like, if you made an 8 gigahertz processor, you would need to cool that thing with liquid nitrogen because it would be so ridiculously hot. So that's just impossible, impractical for consumer grade stuff. And so instead of like making things so fast we couldn't cool them, we started just making more cores to our processors. Now you have like dual core, quad core processors these days and more. And so, what we started to do is like, we got all these transistors, let's just make a bunch of little chips that are easier to cool down, and like we'll put a bunch of processors on our processor essentially, and maybe each of them are about 2.5 gigahertz, but they can do 4 things in parallel because there's like 4 mini processors. So that's what multi-core kind of means, if you've heard of that. And soon enough, Moore's law is not going to apply. We're getting to the end of Moore's law. Sadly, we're making transistors so small that we run into atomic issues, like electrons, or like we can't store transistors hold charge, right? And so you can only put so many electrons in these tiny transistors, and so they're like quantum effects are messing with those electrons at this point, because you can't have very many inside of these tiny transistors. And so eventually we're going to hit that wall, and Moore's law just won't apply at all. But we've done pretty well for ourselves. Here's a graph. Is the graph of the number of transistors on tiny microchips. And let me zoom in. On the x-axis, we have time. We have years, every 2 years, of course. And then on the y-axis, we have the number of transistors in all the chips that are plotted here. And this is a log scale. And so that means if you see a line, if you see a trend line, a straight line, and we do, right? That means there's an exponential increase, right? Because it was a log scale on the y-axis. And so we totally see that line. We totally see a line, and so Moore's law really is applying still. But let's learn some history. So like the very first Intel processors came out in like 71, Intel 4004, 8008. And these were on the level of like 5,000 transistors, so tiny. Large chips, because they couldn't make them small, but tiny amounts of transistors. And then slowly but surely, they learned how to put more and more transistors into things. Motorola 6800, I think, was like in the first Macs, on the level of 100,000 processors. Really cool. Intel coming out with more things. Intel versus Motorola. It's interesting to see that at the time, like, Intel chips in like the mid 80s were like almost like 500,000 transistors, and then you see the ARM chips start coming out. Those are the chips that live inside of all of our phones, modern day Macs and stuff, but they're getting the same speed with much fewer, an order of magnitude fewer transistors, which is very impressive. And so that's a cool thing that you'll learn more about when you get to CSCI 45 if you ever get there. But like the ARM processors, they tried to have fewer transistors and keep the same kind of speed as like the fancy Intel ones. And then slowly but surely, we start getting to billions of transistors. Pentium was a fancy term that came out in the early 90s, and they kept going with that for a while. Lots of Pentium processors from Intel got faster and faster, on the order of 10 million transistors. Pentium 2, this was like starting in the 2000s, mid 2000s, like Pentium 3. All these things, AMD came on the scene, and suddenly, by like the mid 2000s, we've got 100 million transistors inside of our chips, and computers just keep getting faster and faster and faster. And then around here, which is mid to late 2000s, we hit that power wall, and so now you see the things that say core in them, core 2 duos, like dual core processors, quad core processors. That's how we kept keeping Moore's law alive and shoving more transistors, and now we have on the order of billions of transistors at that time. Crazy stuff. And modern day stuff, you can stick 32 cores inside of a processor, inside of some server somewhere. That's totally fine. You got plenty more than where that came from. 72 core processors. And so I should probably update this, but we're at the order of like a few billion, 50-ish billion transistors these days per large server chip. So Moore's law still applies. We still have this scale. You see how there's still a trend line, and so it's still working out for us. But soon enough, this is going to stop. And so it was nice. And so, yeah, it used to be like every 2 years, just like, why improve your program if you're a software engineer? Just wait 2 years and it'll run faster. It'll run twice as fast because the computers will be better. Nowadays, you can't really do that anymore. But it's pretty cool. So that's Moore's law. That's how fast computers are getting faster. Now you know what that means. Eventually, the law will fail. But it worked out pretty well. Yeah, so I wanted to talk about that before I talked about artificial intelligence, because the whole reason like computers can think is that because they got fast. Right? Over time, they got faster and faster. And so let's talk about that. Artificial intelligence is just the idea of like having the computer be somewhat sentient and letting it reason about things in a way that a human might. How good are they at that? So let's have like a bold definition of AI. So artificial intelligence, hopefully you know that's AI for short. That's when machines are doing some form of thinking that's commonly associated with humans. All right. So in some way they are, like a human would, they are perceiving their environment with some sort of sensor perhaps, or like they're getting data from somebody. And then they're making choices based on that data that they've been getting from sensors or from input. And they're using that to achieve whatever goals were programmed into them. Okay? So a very utilitarian idea, artificial intelligence. And there are so many different subfields of artificial intelligence. There's robotics is a big one, like making robots that like perceive their environments, like that can dance and jump up on things and do work for you. The Boston Dynamics company is like a weird one. Maybe you've seen their holiday videos with their weird dancing robots that look like this. Like eventually they're going to be useful, but it's like a research thing. So robotics is a big subfield of AI because the robots need to know how to like do stuff on their own. Machine learning, very popular, of course, subfield of AI. Like you've got face recognition to like look for people and do fancy, what's it called? Do deep fake things, and of course you got your ChatGPT, image generation, all that fun stuff. The most popular kind of machine learning is using what's called a neural network, and I'll tell you more about that. It's like modeling a brain, like a human brain or like an animal brain, with all of its nerves and synapses and all those weird words that I don't fully understand because I'm just a computer science person. And even statistics, at the end of the day, has to do with artificial intelligence, because a lot of artificial intelligence things, a lot of techniques, they came out of statistics. Like I would claim that like the word data science, if you've heard of that, or just even like most fields of AI in general, they are glorified statistics, right? It's just like a buzzword. But really deep down, statistics is what's going on inside of your computers that are performing artificial intelligence, right? They're just reasoning based on like probabilities and things, which is cool to think about. Okay, so let's look at some examples of artificial intelligence. I know you have a few that you know about already. We'll get there. But like I would say the first modern use of artificial intelligence from what I remember growing up is like the first digital cameras. If you remember, like people that used to have, maybe your parents have an old digital camera, uses an SD card or something. What it did a lot of times is it had blink detection. It was able to find faces, right? Everybody's phones can do that these days, right? They have like draw a little box around your face, and early cameras were also capable of detecting if somebody blinked, which was nice. Okay, that is technically machine learning, all right? And so, like, this is what it did. It's like you took a picture, and like there was a person in it. It was able to notice that person. Like it will draw a little box around their face, and then it's also capable of knowing like were their eyes open or not. That is a very interesting drawing of people, but it's able to figure out where their eyes are and see if they were open or not, which is interesting. Okay, so it's able to tell that kind of stuff, and so this is a good first one to like talk about. Like how did they make this? how does machine learning work? How do we build this kind of thing? How do we build ChatGPT? Here is the process. It's a very, very simple thing to explain. It's just the devil is in the details, right? Here is how machine learning works. If you never looked into it, right? What you do, let's pretend. Let's have this as our running example, blink detection. What you do if you want to do machine learning to solve a problem, you make your first step, usually the hardest step, is to make a giant set conglomeration of what's called training data. All right. So if you're going to train a machine learning model, these are the technical terms, to do blink detection, you're going to create a bunch of pictures. You're going to take a bunch of pictures of people, right? You're going to take a bunch of pictures of people with their eyes open and a bunch of pictures of people with their eyes closed because you want to be able to detect the difference. See that? So you're gonna take thousands of pictures, millions of pictures like this. And that's how you're going to train your machine learning software. Right? So you're going to take a bunch of pictures with people's eyes open, a bunch of pictures with people's eyes closed, with a bunch of people in the picture. Eyes open, eyes closed. That's the idea. You're going to take a bunch of pictures and label them like that. And also, if you want to be able to just notice faces in general, before you notice eyes open and closed, you better also give a bunch in your training data, have a bunch of pictures that are labeled with faces, right? And also pictures of things that don't have faces, so that it doesn't like hallucinate and figure like, oh, there's a face in this plane or something and the plane blinked, right? So you have to do that kind of stuff. So that's the thing. You got to generate a bunch of training data and you're going to label it. And you're going to draw boxes where you want it to draw your boxes. You're going to be like, oh, the eyes are open here, the eyes are closed here. All right, so you're going to do all that. And then, step 2, this takes a lot of computational power, but honestly, the hard thing is to get all these millions of pictures of labeled things. It takes a while. Step 2 is to train your model. All right, model is the technical term of your machine learning program. The other name for that, the synonym for that is called your model. And you train it using some machine learning technique. The popular one these days is neural networks. And so a neural network is like a computer version of a brain. And so you have a bunch of the little pieces of a brain, little nodes that exist that talk to each other. Are those synapses? What's the name for that? I forget the word. But you have a little virtual brain, and you have all these pieces of the brain that like neurons. Sorry, I'm dumb. You model little neurons as little pieces that move essentially numbers around. So that's kind of what you do. It's like all a neural network is it's like a virtual brain with a bunch of virtual neurons, and it's thinking in terms of numbers. It's like it's sending the number 1 this way, the number like then it feeds it into like number 2, negative 5.5. Like it learns all these numbers, and then it takes your input picture and like sends it through all this to generate a number, and like maybe that final output number means there was a face. It wasn't blinking or something. That's kind of the idea. All right. So that's what a neural network is all about. I'll tell you more about that later. But usually your model, like it needs to be trained for a while. It's really bad the very first time. Like it thinks that planes are faces and faces are planes. Like it can't figure out the difference. Can't figure out the difference between open eyes and closed eyes. So it needs to keep running on itself and training from its mistakes. And eventually it'll get better and better and better. So this is like, it sounds like it's secret, but it's just a bunch of like re-looking at things, and it kind of figures out what it means to be a face, what it means to have eyes open, what it means to have eyes closed. It just figures that all out from the pixels of your training data. And then finally, you've built this model. It's doing really well on the training data. You want to make sure that it didn't just memorize the training data. Like you could think of like somebody studying for a test and just memorizing answers. They're not really understanding the concepts. You want to make sure that your machine learning model really does detect faces and figure all this stuff out. So what you want to do is you want to save some of your training data and don't give it. Don't train on it. You want to test your model on a separate set of labeled data to make sure that it's like not just memorizing the training data. It's not just memorizing this exact picture of a face. It's like figuring out where faces really are. All right? So that's important too. And then just make sure it's doing well on that, because like it wasn't trained on that data. Make sure it's actually doing it right. Okay. Honestly, the hardest part is step one. It's usually very, very hard to get a lot of good training data to be used. And so now you know why a lot of services are free that shouldn't be free. Google Photos, if you used that before, it used to be free. You could put all your pictures and videos on it. That's because Google was training their machine learning detection tools on your pictures. Facebook pictures, Instagram pictures, it's all free, probably because they're going to train machine learning techniques with your data. So that's an interesting thing to think about. So that's, in a nutshell, that's how machine learning works. Now you can go watch like a YouTube video or something and understand more. So yeah, neural networks are the cool thing, the hot new thing these days. And so I want you to learn a little bit more about them. But first, I just want you to play around. If you've never really played around with this kind of stuff, you haven't even tried ChatGPT, maybe. I want you to let's play around with some image generation. So, if you could please, just for a few minutes, go and have fun with the people sitting next to you. Go to this website, crayon.com. And it has AI in the words, spelling crayon wrong. Crayon with the AI, which is kind of cute. And then what you can do there, if you've never used this before, it's an image generator. So you give it what you want to generate. It's like, I don't know, whatever. A cat, I don't know, sniffing a flower with a rainbow in the background. You give it whatever you want, and it will draw that for you. And just play around with that website for a couple minutes, and then we'll feel free to share your fun pictures on our Discord if you like. But it takes a minute to think about it, and it will eventually generate pictures for us. And so as you play around, I want you to think about what kinds of training data do you think they used to get this to like take your arbitrary text and generate images. Think about that while you try it. But it's going to take a minute to do its thing. And if you know another website, feel free to use that one. There it is. Look at it. Oh, why can't I scroll right now? Something's wrong. I swear it's here though. Like here's a picture that it generated. Look at them all. So these are just like it's coming up with cats, and it's coming up with it knows what a cat is, it knows what a flower is, it knows what a rainbow is, and somehow able to put that all together and make interesting looking pictures. That's pretty funny. So yeah, as you try that, give it a few minutes to generate, but like what kinds of training data do you think they were using to build that? Just like think of the inputs and the outputs. What did they need to make that happen? Because you got to give it a bunch of stuff that it's going to eventually like similar to what it's trying to generate. Huh. So I'll give you a minute to play around with that, and then we'll come back and we'll try another one. That's a bit more educational. None of those pictures were ever made before. I was able to figure out what a cat is, what a rainbow is. How? How do you think? Feel free to share your funny pictures on our Discord or something. But like, what did they do? How do they figure out? How do they make this? How do they train it to go from these words to pictures? Well, the secret. Dun, 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 I really would like to fix whatever the issue is right now. Why can't I scroll? Maybe I can just have it scroll for me if I delete an element. Or if I zoom out, maybe now it works. Who knows why it won't scroll, but that's okay. It works. What else was I going to say? So yeah, it's able to go from these pictures, or this text to pictures. How did it do that? What was its training data? Well, it was just a bunch of pictures, right? This was trained on a bunch of pictures that had sentences labeling them. Does that make sense? So it had like millions of pictures that had the word cat in the description. And so it was able, with its machine learning, to learn what it means to be a cat. Does that make sense? It had a bunch of pictures trained on with like descriptions next to them of rainbows. And so it learned what it means to be a rainbow. Yeah? It learned what it means to be a flower. And like it eventually learned what it means to like have English as well, like the descriptions. It learned like rudimentary ideas about English, like prepositions and things, how sentences are structured, because it was given a bunch of pictures and descriptions of those pictures. Does that make sense? If you have a bunch of those, it will eventually learn. We're talking like millions of pictures and descriptions of those pictures. You have enough of them, it's going to learn how to do it, how to build back new things with those same ideas. Isn't that cool? I hope that makes at least a little bit of sense. So, let's see, I promised to stop that. Let's keep on trucking with a new example. So here, please go to this website, and this is going to teach you. This was trained, any image generation these days is trained using neural networks. ChatGPT is using neural networks. Please go to playground.tensorflow.org, and this is a more educational example of what a neural network is. All right. So please go to this website, playground.tensorflow.org, and I'll show you a little bit about it. But the idea is a neural network, which is what every fancy piece of artificial intelligence is based on these days. It's a model of a brain. It's a computational model of a brain with neurons, right? So little circles called neurons, essentially. And what they're doing is they're learning weights, things called weights, which are numbers associated with those neurons. And so it's taking input somehow. You're giving it input, and it's feeding around numbers. Like it's using this neuron, it's using this number, and it's feeding into a new neuron that does something with that 1.0 and the 2.0, like adds them and does some sort of nonlinear operation on them, if that makes any sense to you. So like you can hook up these neurons any way you want, and then like it's going to take the previous input and do something with it. And it's going to feed along those numbers in a certain way, and it's going to learn like what all these numbers attached to these neurons mean for some sense of meaning. And eventually it's going to output something. It's going to output another number that you can use to like say if there's a cat, say if there's a rainbow, say if somebody blinks, say if there was a face. So it's just shuffling around numbers. That's all it's doing. It's learning how best to shuffle around numbers. And some of these little individual fake neurons, like they're eventually going to learn different pieces of what it means to be a face, what it means to be a cat, stuff like that. Okay, so here is the idea. Here's a bunch of different data sets that you could learn. Here's the first data set, for example. Like there's a bunch of blue dots, and then there's a bunch of orange dots for all of these example data sets, blue dots and orange dots. And the goal of this particular machine learning educational page is like train a neural network to discover the difference between the orange dots and the blue dots. All right. So what you can do is you can give it inputs. You can give your neural network different kinds of inputs. You're giving it a dot essentially, and you're having it figure out if it was green or blue, blue or orange. Excuse me. So you're giving it the input is always a dot, and here's what it means. Like you can give as inputs. X1 just means the x coordinate of that dot. X2 means the y coordinate of that dot. I know it sounds a little weird. X12 is, let's see, it's the squared. It's the squared first coordinate. So it's the x coordinate squared. X22 is the y coordinate squared. X1, X2 is their multiplication, if you need that. You can feed it the sign of the x coordinate, and you can feed it the sign of the y coordinate. Those can be inputs to your neural network. You can turn them on or off. Right now, it's just the x and y coordinates selected. And then you can have little neurons. You can have little bits of neurons. Those are the ones in between are called hidden layers. And then you have an output layer of neurons that eventually give back a number that determine whether or not it saw orange or blue, right? And so just try to play around. You can keep these things up here the same, but if you click the plus button and you've generated your neural network, it will try to learn the difference between the orange dots and the blue dots. And it will draw a picture of how it's learning it. Whee! There it's going. And so it's slowly but surely trying to figure stuff out, and the different neurons are learning different things. Like this neuron right here, you can kind of see how it's learning this kind of line between the oranges and the blue things. This one's learning this kind of line. And then as it gets further into the system, it's like learning more interesting things. Like it's combining these two things and learning like a little curve in the middle there. This is learning like a little curve between orange and blue in that sense. And then by the third layer, it's starting to like combine these in a certain way to like figure out circles. It's trying to learn what it means to be a circle. You see that? That's so cool. Just out of nothing, it's learning circles. And so it's getting really good, and you can stop it. And it's like it's learned this shape that differentiates the blue dots from the orange dots somehow. Isn't that really cool? So yeah, that's the idea. That is the problem. So like given inputs, compute outputs. And so I'd like you to play around with these other training data sets and see if you can make the smallest neural network that generates that has really good results. Right? So like how would you train a model to figure out the difference between these orange dots and these blue dots? You want the model to learn like a line, right? To learn a line that draws a separating thing between them. So maybe you don't need many layers, because like even the first layer is figuring out lines, right? So think about that. Try it for all these. I'll give you a few minutes to play around. But yeah, it's usually possible to get to work if you just select everything, have as many hidden layers and neurons as possible. The game will be try to have the fewest number of neurons. It's computationally intensive to have a large neural network. You want to save your boss money or something. Yeah, play around with that for a few minutes. It's a fun idea. I'll give you a couple minutes and then I'll show you the secrets. The swirl is the hardest one. And this one's not too hard. This one's okay. This one's like you got to learn a checkerboard pattern, kind of. But at the end of the day, you can see, I go back to this example, I retrain it. The numbers that it's learning are called weights. So you can see like thicker lines to mean that those neurons were more important. Like this was a high weight. It was being passed along. So it looks like, like this. In this last layer, this third one was very important. It was getting a lot of weight into the next layer, which is kind of cool. Some of them are learning circles better than others. But at the end of the day, it's outputting a number. It's outputting a number between 0 and 1. It's like below 0.5, it means orange. Above 0.5, it means blue, and that's how it's like using a number to talk about it. Let's try to figure out that difference. See if you can get it to work. So yeah, when you're doing machine learning, it's usually best to start small because you run the risk of what's called overfitting when you do too much, like you have too many layers and too many neurons. Because just looking at the orange dots and the blue dots, like what really separates these guys? It's not this weird looking blob thing. It's a circle, right? A circle is the real thing that separates these dots. And all we really want is this network to learn what it means to be a circle. Yeah? And so remember the equation for a circle, it's x squared plus y squared equals r squared. We just kind of want it to learn this. And like if you give it x squared as a neuron and y squared as a neuron, it'll combine that in the next layer. And that's pretty much it's learned a circle at that point. So here's the secret. I can have 0 hidden layers, 1 output neuron, and if I give it x squared, that's x, this is x1 means x squared, and if I give it y squared, it will add them together in the output layer and generate the equation for a circle. Bam. Very, very simple, see, neural network at that point. So that's a lot less computationally intensive. So there is an art to it, in a sense. You can also just throw neurons at the problem a lot of the time, and it will work. But this is like one way to make that one work very quickly. This one, how would we make this one work? We've got a checkerboard pattern. It's blue when the coordinates, if this is like 0, 0 in the middle, it's blue whenever there's like, they're both positive coordinates or both negative coordinates, and it's orange if one's positive and the other's negative. See that? So if you just multiply together the two coordinates, they'll like cancel out the, like down here in this quadrant, the negatives will cancel each other out and they'll both be positive again. So that's how you can learn that very quickly. See that? So that's, think about your inputs to make things happen. For this one, you need to learn the equation of a line, and then the equation of a line is just y equals mx plus b or something. And so like you need x and y added together, and it will just learn a line in the output layer. So yeah, it's okay if you didn't understand any of that, but that is, like, you want to keep things simple at the end of the day. For a swirl, like sines, technically, sine is technically going to give you a swirl, but like this is a little weird kind of swirl, so it's not really going to fully learn it very easily. Sine is for spinning, right? It's for circles and things, but at the end of the day, you just kind of need a bunch of everything. So this is kind of the one that you throw neurons at the problem. Whee! And eventually it'll figure it out. So this is totally not a normal equation that you could write very easily. But it will still figure it out. It will still learn the answer. It'll just take a lot more training, and it'll look very weird. It might overfit. But it'll get there, it'll figure out like, oh, this was a very important weight right now. It's really helping me. But it's kind of like stuck. And so, yeah, if you let this run long enough, or if you start it over again, eventually it figures out the answer. But it really does take a while. So it's getting there. It's trying stuff. It's trying new things. Getting slightly better. Then it's getting worse. But you see it's slowly coming up with a weird mathematical formula for what it means to make all this happen. And that, if you want to learn something complicated, that's kind of what you got to do. So hopefully a fun example. Feel free to keep playing around with that. But now you know a little bit more about neural networks, which are the backbone of all of artificial intelligence. And so do yell at me if you have any questions about stuff, but let's keep on trucking. Let's talk about places that artificial intelligence has like really gone off. So like factory robots, huge deal. Like you got little robots that can do very precision things and build cars, for example. So machines are very good at doing the same thing over and over again, right? They're really good at, like, they're never going to get tired, right? They're not going to fail very easily if they're strong. They work faster and more precisely than a human ever could. Why this says every, I don't know. Than a human ever could. And the only issue is, like, they cost a lot of money to build a purpose-built factory robot. But the second you have it, like, it can go and save you a lot of money. But so this is like, there's a trade-off between buying a robot and then like having that replace people, which is unfortunately a thing that happens in factories. So that's the thing. One cool thing that you may have seen, this feels like artificial intelligence, is you guys remember the Watson supercomputer that was on Jeopardy? Have you ever heard of that? It's been a while since they did that, but this is like a cool idea of an intelligent computer, artificial intelligence. So Watson was a supercomputer made by IBM back starting in the early mid 2000s, and what it does is it used what's called natural language processing to like figure out the questions that were asked of on Jeopardy, for example, and answer them using their giant database of information. And so, like for example, it was able to hold on to the entire text of Wikipedia as it was answering these questions, which is very helpful, right? And like it could think and come up with its answers much faster than any person that's even really good at Jeopardy could do. And so, highly encourage you to watch this if you have not seen it happen before. But yeah, it just uses natural language processing to like come up with like, what is this talking about? What is this question asking? Like, what's the subject? What's the verb involved? Like, it's able to process the sentence in a way that we know how to do as humans, just naturally. And it comes up and it uses its database and it tries to figure out answers, just like kind of ChatGPT does, right? It comes up with a bunch of answers that it thinks might be correct. Let me spell answer correctly though. Answer one, answer. So here's a question like, here are some possible answers for that question. And it's also doing statistical analyses. It's like, I think that with a 91% chance, this is going to be the answer. I think with 85% confidence, this is going to be the answer. Maybe 5% confidence, this is going to be the answer. So stuff like that. Maybe percent is the wrong number to use here, but it's like it just picks the most popular one that it thinks is going to work if it's above some threshold. Like if it thinks it's 90% confident that this is an answer, it's going to give it. Otherwise, it'll just skip the question. So yeah, that's Watson in a nutshell. And how do you train it? It's like, all right, give it a bunch of Jeopardy questions, give it a bunch of answers, things like that. Give it a bunch of trivia questions. Have it figure out, have it learn how to search through its own database, which is really cool to think about. Okay? So there's that. What else? A very, very popular thing when artificial intelligence first, came on the scene in, the 60s and 70s was, wouldn't it be so cool to make a computer that could play chess better than any person? And so, that was the dream for so long. And, in the 90s is when they finally achieved that dream. All right, but this was a huge deal to the early artificial intelligence researchers. Back in 97, that was when the computer, for the very first time, somebody made a machine learning thing that learned how to play chess so good that beat the world champion at the time, which is really cool. And kind of what happens when you're making a machine learning program for chess or for another game that kind of works similarly is you have your current game board. It's what people are doing when they play chess. Here's the current game board. This is where all the pieces are right now. And then say that it's your turn. It's here are all the different moves that I could make. And then you all right, here's what the board would look like if I made this move. Here's what the board would look like if I made this move. This is what the computer is doing. It's generating all these different possibilities. And then it's going down all of those possibilities. It's all right, if I made this move, here's how my opponent might counter this move. Dun, dun, dun. Here's what the board might look like here and here and here. And it just does this to so many levels and to such a degree that it can think ahead so much more than a human could. And then it learns, essentially, what it means to make a good move in chess. That's how it works. Another game that's been popularized more recently is a game called Go. It has a whole lot more states than chess does, and so in 2017 is finally when it beat a world champion, and that was a big moment for artificial intelligence researchers as well. So look into that if you're interested. But a cool fact about how to make a machine learning model that figures out how to play chess well, that figures out how to play Go well, figures out how to play any game well, is that you can just give it all the rules. The rules of chess are super clear, right? You can just list them. It takes a few pages. It's done. But the second you list them, your machine, it knows which moves are valid. And then what can it do? Your chess game machine learning model, it can just keep playing millions of games with itself. See that? That's very powerful. because it knows like all the different moves that could be made. It can keep playing against itself to figure out strategies that have maybe never been invented before. Isn't that cool to think about? The second you give it all the rules and you give it a way to learn, like with neural networks, for example, it can start playing against itself and figure out the better ways to do things that maybe nobody has ever written down before. And so that's what people think caused it to win the game Go. Like it made some weird moves, but they ended up like working out really well in the end. So, yeah. Any questions about that? That's chess. That's Go. Super, super important stepping stones on our way to like perfect computer intelligence systems. Pretty fun. So yeah, that's all that I want to talk about for today of the normal lecture stuff. The last thing that I want to say before you go is kind of like an example of like the kind of stuff you'll do in your essay that you're working on right now. So there's so many fallacies. Like just go to Reddit, go to YouTube. If you don't have a social media account, it's fine. Comments are there too. But like here's an example from Twitter that I found a couple years ago. Here's an example of a straw man fallacy. This is kind of what you would do in your essay. So here's an example. Let's see here. So around this time, it was just International Women's Day recently again, right? So back in 2021, the vice president sent out this tweet on this International Women's Day. I want to honor the women who for over a year have gone to work, often risking their health to nourish and protect us, etc., just like celebrating International Women's Day, right? And then this person, Dave responded, just the women? Guess that would be typical of you. I thank all who risked life for others. All right? And so this is how you'd do this in your essay. This is, you'd say that this poster, like you quote it, you give the context, you'd say, all right, this is an example of a straw man fallacy because this poster, Dave C., is putting words into the vice president's mouth. The vice president is trying to, for the occasion of International Women's Day, highlight specifically the work of women, but that does not mean she was trying to diminish the work of men or anybody else of any other gender. Okay? Just because it was International Women's Day, did she want to do this and like point out the things that women have done? And she was not trying at all to like beat down the things that any other gender has done. Okay? For that reason, she this argument is trying to argue against something that didn't really happen, trying to put words into the vice president's mouth, and that is what it means to be a straw man fallacy. Does that make sense? That's the kind of analysis you do in your essay each time you find something. Okay? Any questions about that? So hopefully that helps you like understand what you need to do. Remember to name your fallacy and all that. But yeah, I think that's everything that I wanted to say there. So yeah, I think you have all the assignments out already. So that is officially all that I have for us today.